Hi, this is Robert Quimby, and I'm going to tell you about telescopes. So in this quick tutorial today, we're going to talk a little bit about the different types of telescopes that are available to astronomers doing research. We're going to talk a little bit about how they work, what they do, how they take light in and produce the images that we report on our detectors. And we're going to talk a little bit about the most common configuration for a telescope that you're probably going to encounter in your research career. So let's begin with refracting telescopes. This is the basic type of telescope that you may be familiar with. This is not so commonly used in research, but there are some applications where they are still used. So of course, the way a refracting telescope works is that it has optics in it, glass lenses, and light comes in through the top. It goes through a big lens in the top, and then there's some smaller lenses inside, and those focus the light down here where your detector is, and you form an image here, and you can record it if you have a camera there. So this is the telescope. This is the detector here. The advantages of a refracting telescope is that it's easy to get very wide field of view. So surveys like this example here, this image is of one of the cameras that was used in the Dragonfly experiment. And that's looking for low surface brightness galaxies where you need to cover a very large area of sky in one shot. So this type of camera is great for that. But the disadvantage is you can't make them it's very difficult, I should say, to make them with large apertures. So you gotta imagine that inside there's this glass lens. And for a camera like this, it's about this big. And you can only support that around the edges, right? Think about that. And also light has to go through this, so the quality of the glass that you're using has to be extremely pure. So you need pure glass this big, and you have to support it around there without putting any stress on that, or else you're going to bend the glass and change the figure of it, and that'll ruin the properties of the telescope. So that's for a lens this big, it's pretty difficult to do. For a lens this big, it's really difficult to do. And if you add that out, if you keep expanding that out to say 1 meter, now you got a really big heavy piece of glass, and all of that area has to be very optically pure, and you have to support it against its own weight and move it around in the sky. It gets really hard to do. So the biggest lenses that are available top out at about 1 meter. And beyond that, this type of telescope is just simply impractical. So most of modern research is done with reflecting telescopes. And you probably know how these work as well. Light comes in from the top of the telescope tube, and it goes down to a big mirror in the bottom. And this defines the collecting area of your telescope. It's the size of the mirror down here. Not the aperture up here is less important, but the main thing here is how big is your mirror. And then what we want to do is that we have some figure on the mirror so that it makes rays converge and go to a focus. And that's where we put our eye or our detector or whatever we're using to measure the light. There's different variations we can do on a reflecting telescope. You can have the light come to a focus inside the tube like this, the prime focus. That's a very handy way to conduct observations. It does have the major drawback that your instrument, maybe your head, if you're just doing this optically, is going to be inside the tube now. So it's going to block light that's coming down. So clever guy Newton had this idea that, hey, why don't I just put a little mirror in here, and then I can just block a little bit of the light, and then the rest is going to go through, bounce off the mirror, and then come out a port here on the top where I can look through the eyepiece. That's a great way to do it. So this is very popular among amateur astronomers. This is a nice design for that. The issue with this for research is that if you're going to mount, let's say, a big heavy camera or a spectrograph at that port right here, it's going to throw off the balance of your telescope. So it's going to be very difficult to balance the telescope with something heavy on the end like that. We'd prefer to put the heavy stuff down here where there's already heavy stuff, which is usually where the mirror is. So one of the more common designs you'll see in telescopes, amateurs and research alike, is a Cassegrain design. So in this design, that primary mirror actually has a hole in the middle, and you put a mirror inside the tube. So again, you're blocking some of the light that's coming through the top of the tube, but not too much, hopefully. And you're reflecting these off the primary mirror, and the secondary mirror here reflects the light back through the Cassegrain port. And you can put a big heavy instrument here at the end of the telescope, and it's much easier to balance. There's a further variation of this design where you put in another mirror, so you have a tertiary mirror, and then that mirror can kick the light off to the side of the telescope, And this has some handy advantages because often we have mount points that are holding the telescope to the mount right about here. That's kind of the natural balance point for the telescope. So you can have a big arm that's supporting the tube of the telescope and then put light through that arm and have it go to another room where you have an instrument that's just sitting on the ground and it actually never moves. So if you have an instrument on the Cassegrain focus as the telescope moves around, that instrument is moving around and it's changing its gravitation vector and causing different stresses on the instrument, which can possibly warp your images. But if you take that instrument and you put it in a Cadet or a Naismith focus, then in principle you can just have it permanently mounted on a bench somewhere and it never has to move. The instrument never has to move. All right, so the primary thing that telescopes do is they collect light, right? So the bigger this aperture is, the more light you're going to collect and the fainter objects you can study. The other thing that a telescope does is it magnifies the images from the sky. So let's talk a little bit about now how this works. So the very first thing you got to think about is that light is coming from a source for an astronomer that's very, very far away. So if you think of just a point source, like effectively a star is a point source because it's so far away, those light rays are coming all in parallel. They're all coming straight. By the time they arrive to the detector, the light we get is all moving effectively parallel. So these parallel lines, these horizontal lines here, are from one source, and these lines at an angle here are from a second source. So two different sources on the sky separated by some angle theta. And what we want to do is we want to consider how that separation is going to be registered at our detector or eyeball or whatever. How far apart are those going to be? So this schematic here is kind of looking at it's a schematic version, so it's kind of an idealized version of the telescope here. In this design, we just have one aperture here where light is coming through, and we have some focal plane here where we're going to have our detector. So, this is where your eye is, or this is where your CCD or your camera is. Now, the way it's kind of laid out here is kind of looking like it's a refracting telescope, like we have a big lens maybe here that's collecting light. But if you just allow yourself to imagine this line here of symmetry, you can just fold that over and you can have yourself a reflecting telescope. It's the same thing. So we're going to use this to represent actually either a refracting or a reflecting telescope. So light comes in through your primary optic here, your aperture, again, which is a lens or maybe a big mirror. And it's coming from different sources that are separated at different angles in the sky. And we're just showing two different sources here. And what you can see is the bigger this aperture is, the more of these parallel rays you're going to detect. Right? So it's very important to understand that this line here and this line here and this line here all came from the same source. And you can appreciate this if you go outside and you look at a star and then you move a little bit to the side, you still see that star. You move over to the side, you can still see that star. Right? So that's what's happening here. You're going to light from the same star in the same parallel rays, just over an area, and the bigger you make that area, the more of those photons from that one source you can get. Now, when the light rays go through your aperture or reflect off your mirror, they get bent. That's how a telescope works. It bends the light. It changes the angle from the incident angle to some reflected angle. And what we need to know now is how does that light end up on our detector? So you can see these lines drawn here. So we're, again, considering two different sources. So a light ray that goes in straight for our detector just goes through our aperture. So I go straight through to the detector plane, to the focal plane, like that. Lines that come in over here are going to get bent and focused here. And a line that's here is going to get bent and focused here. So no matter where we go in this focal plane, we want all the rays of light that we had at the aperture coming together, converging at one point. And for a different source, we want those light rays to go to a different part of a detector and only there in that spot. So what we can see is happening here is that we are creating some separation S here between one point in the sky and another point in the sky. And these are separated by some angle here. So we now have some relationship between what this angle is in the sky and what the separation is on our detector. And this turns out to be a function of this focal length here. So the longer the focal length is, the greater the separation is going to be. The way we can work out what this is we can note we have a nice right angle here. So we have this line here, which is just F, and this height here, which is just S, and this angle here, theta. And if we put these numbers together, we can calculate what's called the plate scale. The plate scale is just this relationship between that angle, the angular separation on the sky, and the linear separation on our detector or focal plane. It's usually measured in arc seconds per millimeter. So what we can do is we can use our trig here. We can notice that we have this nice little triangle. We can use a small angle approximation because these are the field of view for the typical telescope is just going to be a fraction of a degree. So we're well into the small angle approximation zone here. And then all we have to do is just convert from radians into arc seconds. And when we do that, we work out this number here, 206,264, which is a number, if you ever do any optical work, you're going to see this number a lot, because that's going to be used to convert our angular scale into a linear scale, a plate scale. So all we have to decide now is what figure do we want on our mirror or objective lens so that we can get all the light from one source at one point on our detector. What shape do we need to have here so we get this bending from this ray to this ray to this ray, this one going straight through and this one to this one, so they all focus here. So to do this, let's first talk about conic sections. You may have studied this in the past. There's a cool thing you can do. You can take a cone, right, and you can cut it parallel to its base, and you can make a circle. That's the cross section turns out to be a circle. If you cut at an angle, slight angle, you're going to get yourself an ellipse. And if you cut it at a great enough angle, eventually what you'll get is a parabola, right? So this is now an object that starts, a shape that starts together at one point, and these lines go off and they diverge. They never actually come back together like an ellipse. They keep going off and off to infinity. And if you have an even greater angle on your cut there, you can get yourself a hyperbola. This is kind of a graphical representation. We can actually use a little algebra to define these shapes a little bit more precisely here. And what's to note is there's two important values in here. So we're just doing an X and Y plane here. And then we have two constants that we care about. R is the radius of curvature if we have a circle. So if we have a circle, R is just that radius from the center to the edge. And then K here is our curvature constant. This is very important because that's determining whether we have a circle or an ellipse or a parabola. So the way it works here is if we take this equation and we put K equals 0, we're going to get ourselves a circle. If we put K equals -1, this term disappears, and we just have an X term and a Y squared term, and of course that's a parabola. Right? And so if we change K to an even more negative number, like -1.1, 2, 3, whatever, then we're going to get ourselves a hyperbola. So the parabola is this critical line here. If we're a little bit less than -1, we're actually going to, eventually that curve will come back together and we'll get ourselves an ellipse. And we can also have a value that's larger than 0, but positive, and that's going to give us these oblate ellipses. So let's actually do an example now. We're going to put this into practice. We're going to do a ray tracing example. So we're going to try different shapes for our primary mirror and see where the light comes to a focus. So I've put together a little bit of code here. The important thing is we're going to define the shape of a mirror based on our curvature constant, K, and the radius of curvature for our shape. And once we define those two quantities, we can define the curvature, the shape of our mirror. Then what we can do is we can ask when a ray comes in, it's going to bounce off at a different angle depending on what the slope of the mirror is at that particular Y point. Right? So I'm assuming we have a mirror that's kind of symmetric about the x-axis, so it's just sitting up in Y. And if a photon comes in and bounces off that mirror at a different Y position, it's going to have a different angle, so it's going to reflect off at a different angle. So these define my mirror here. So we can do that. And then we have some other functions here, one just to draw lines in different colors. and one to actually make the plot, so to draw a line where that mirror is, and then we're going to actually have it draw lines coming in, incident lines, and show where they reflect off. So this is our ray tracing function here. So I'm just going to run that cell, and then we're going to try it out. Okay, so let's start by just plotting our mirror, and we'll just have some incident lines coming parallel, and they're going to reflect off, and we'll see where they go here. So we'll start off with a curvature of -1. That's a parabola. It's an interesting shape if you know how this works out. For making a mirror, we're going to set the radius to 4, and we're going to start by just showing just the mirror itself. So if I run this, there we go. So this gray thick line here is our mirror. Again, this is just just a slice through it, kind of a 2-dimensional slice. It's actually a 3-dimensional object. So you got to picture it rotated around. This dashed black line here is an important line. This represents our optical axis. So we have everything aligned so that right here at the center here, this point is tangent. So if a light ray comes in through here, it bounces off straight back like that. So this defines the optical axis for our system. So what we're going to do now is add some other rays of light. This one by itself is not very interesting. So let's add some incident rays. And there those are. So now we have all these different colored rays. Each one of these represents one ray, and they're all running parallel now. So they're all parallel to each other, and they're also, I've drawn them parallel to this optical axis. We'll change that in a little bit. But for starters, each one of these is coming and hitting the mirror at a different point. The slope of this mirror is changing as a function of y coordinate here. So we have to calculate what the reflected angle is at each one of those. And if we do that, we can see where these lines go. And that's how that works out. So these input rays come in, bounce off the mirror, and they all come and cross, no matter where you go, at this point right here. And that's the focus for our parabola. Now, you've probably seen this before. You've probably seen that parallel lines, when they hit a parabola, they all go together and they end up at a common focus here. What if we use a different shape here? So instead of using a parabola, what if we used a circle? So with a curvature constant of 0, we can get ourselves a circle. I'm going to go ahead and turn off the incident lines here because they're just going to be all parallel. We already know what they look like, and it'll make it a little easier to see. And if we plot now what we get with a spherical mirror, this is what we get. So here we have our spherical mirror. Light rays are coming in. They're not drawn now, but they're bouncing off the mirror at different points. And all of them are going to about the same spot. But you'll notice they're not all going exactly to the same spot here. So we can change the limits here. Let's just zoom in a little bit to make this even more clear. So we'll plot x lim going from 1 to 3. And let's do our y lim going from -1 to 1. There we go. So we're just zooming in here. So the way that a detector works is you're going to put in you put your eye in this field of view, or you put in a detector like a camera, maybe a CCD. It's going to be somewhere in this plane here. So if you have like a CCD, it's very flat. It's a very flat structure. And so what you can see is that as you move across the y-coordinate here, you're going to go into different pixels on the detector. And so effectively what's happening here is light coming in from different parts of the aperture of the telescope are getting reflected off the mirror and going to different parts of the detector. And that means if you take an image with a spherical lens, you're going to get light distributed around a whole bunch of pixels when they're all coming from one source. That's going to make basically fuzzy images. There's a particular name for this type of fuzzy image. So you can see that most of the light is going to go towards a common area. And then as you move farther out from there, you're going to get fewer and fewer photons. So what we can do is the effect is you get a kind of a bright spot in the middle with kind of a halo around it. Not a halo, kind of a slow decline, kind of a haze around it. So we call this spherical aberration. That might be a term you've heard before. It's a bad thing if you have optics and you have a spherical aberration. It means you're not getting light focused to a point like you want it. Let's contrast this again with our parabola. So put in -1 here. And then you can see that boom, right on the optical axis. So we have rays, again, that were parallel to the optical axis, and they're being focused on this optical axis here, all at the same point. So if we put a detector across here, all that light is going to go into, let's say, 1 pixel on our CCD, and that's what we want. let's back out now. And let's look at those incoming lines again. Let's recall something. All of these lines are coming in parallel to themselves, of course, because they're at a from a distant source, but they're also parallel to the optical axis here. So an important consideration is what happens when we're looking at an object that's the telescope's not directly pointing at. What if the telescope's just a little bit off? So it's just maybe another source still in the field of view, but maybe a few arc seconds or maybe a couple arc minutes away from our source. So we can simulate that here just by changing the slope of those lines coming in. I'm just going to make them a little bit offset. Let's turn off the reflected for a second. There we go. So now all these lines are at a slope of 0.05 with respect to this optical axis here. And so the question is, when they bounce off, where are they going to end up? Right? So think about this for a second. This is kind of an important point. Stop the camera, stop the video if you need to, and just predict in your head, where are all these light rays going to end up? All right, let's see where they end up. There. So a couple things you can see immediately from here. One, the light rays don't focus on this optical axis. This is what we talked about before. When you have an object that's at some angle to another object, they're going to land at different parts in your detector. So we're seeing this now, this kind of separation of sources from angular separations into linear separations on where our detector plane is, or focal plane. However, you'll also notice if we zoom in here, and I can turn off the incident photons here, incident rays, that again, the light is not coming to a focus at a single point on a detector. So this isn't always covered when you talk about parabolas. People talk about incoming rays that are parallel and parallel to the optical axis. But when they're offset from the optical axis at some angle, they don't focus at a point. All right, so this is important for our telescope design. This means that if we have a parabolic dish, a parabolic mirror for our primary mirror, light rays are going to be focused if we're in the center of the detector perfectly on the optical axis. But as we move away from there, they're going to be more and more distorted. The images we receive are going to be more and more distorted because that light's going to get spread over more and more pixels. And again, there's a particular way in which this happens. If you look at this, most of the rays are going to be focused on one small area of the detector. And as you move away from that in one direction, you're going to get light. But the other direction, you don't get that. So what you end up getting is kind of a bright spot with kind of a faint tail to it. So this type of reflection, this type of aberration is called coma. Okay, so we don't want this. We want light to come to a focus at a point no matter where in the field of view we are. So if we have a source in the middle, we have a source offset at some angle in the sky, and we want both of those to fall on our detector, we want both of them to be in focus, and all photons just going into a small number of pixels on those. So how do we do this? There's different ways to accomplish this, but one of the most popular ones is this design here. This is called Ritchey telescope. I'm not entirely sure I'm pronouncing that right. A lot of people also agree with me, so we just often call these just RC systems. So this is an RC design here. And the way it works is, instead of having a parabolic mirror, we actually have a hyperbolic primary mirror. It's very close to a parabola, but technically a hyperbola. So we have a hyperbolic primary here. Light bounces off that and goes to a secondary mirror. This secondary mirror is not a simple flat mirror, and it's not a parabola either. It's again, another hyperbola. You also notice that the hyperbola here is convex. The primary mirror is concave, so light comes to a focus. It's bringing light to a focus. It would focus out here somewhere, but it hits this mirror, which is convex, and that slows down the beam. It slows it down and makes it focus farther away. So this distance from where the light hits here to where it's focused on the detector is much greater than where this focus would happen. So the the curvature on your primary is not setting what your effective focal length is for your telescope. That's the combination of this primary mirror and your secondary mirror for an RC system. So the idea here is that by having these specific hyperboloids for our mirrors, for our primary and our secondary, we can actually counter the effects of coma and spherical aberration and produce images that are more, not perfect, but more sharp, even as you move away radially from the optical axis. It doesn't work perfect, but it works a lot better. It's a very simple design to correct for coma in spherical aberration in one go. And this is the prescription for that. So we have to have what those K constants are for our two mirrors. And this is how it works out. If you use so you have these different distances. You have the diameter of your mirror, you have the focal length, and you have the back focal distance, the distance between the detector and your secondary mirror. So if you work all these out and you get these constants K1 and K2, then you can prescribe your optics, your secondary and your primary mirror to meet that, and you'll get yourself an RC telescope. This, again, is a very common design. This is the design that we have at our telescopes, like the 1 meter telescope at Mount Laguna Observatory. It's also what major telescopes like Keck have, and even the Hubble Space Telescope is an RC design. So I hope this gives you some idea of how telescopes work, and hope you can think through this and think about what would happen, for example, if you put a hand in here and blocked out some of these photons. Would you see a hand at the focus here? I'll let you think about that and think about the other things we covered here, and enjoy.